Much of astronomy is about light. Most of the information we can glean from the universe comes from studying the light we receive from space. Even when we send a spacecraft to another planet, most of the instruments on that spacecraft will still rely on studying light. Matter is what all of the objects we want to study are made of, so we need to have a basic outline of the properties and structure of matter. In this chapter, we'll look at both light and matter and how they interact. We'll start by looking at the properties of matter. We'll look at atoms and their properties. We'll talk about the phases of matter. And finally, we'll discuss some of the bulk properties of matter that we can measure. Then we'll look at light. We'll start by looking at the properties of light itself. Then we'll see how light and matter can interact with each other. This last part is where we'll start to see how we can use light to measure the properties of matter, as well as how light can affect matter. Both of these will be important later in the course. Around 200 years ago, chemists started arguing that matter is made of discrete particles called atoms. This was already a very old idea. The name goes back over 2,000 years. But by the late 1700s, there were several experiments that strongly suggested that atoms were real. We now understand that atoms are incredibly small, typically 10 to the minus 10 meters across. This means if you made a line of 10 billion atoms, it would be only a meter long. Anything big enough for you to see without magnification is likely to have trillions of atoms or more. Chemists also realized early on that not all atoms are alike. We now know of over 100 different kinds of atoms, known as the chemical elements. Some of the elements we run into often include helium, iron, and carbon. Do you know where the purest carbon in that pencil is? Think about it, and I'll tell you shortly. There's also aluminum and gold. This last image is also gold, but seen at high enough magnification that you can just begin to see the individual atoms. Okay, what about that carbon? It turns out there are 3 different pure forms of carbon. One is something called buckyballs. You get a lot of those in soot whenever you burn something. Another is the form you get in the pencil. Graphite is pure carbon, and it's what the lead of the pencil is made of. There's a third form of pure carbon, but it's a lot rarer than the other two. It also has a very regular crystal structure, which makes it both very hard and almost transparent to visible light. Can you guess what the third form of pure carbon is? If you said diamonds, you're right. Just think, the raw material for making diamonds is sitting in your pencil box. In the middle of the 19th century, a Russian chemist named Dmitry Mendeleev noticed that there was a pattern to the chemical elements. If you started listing them from lightest to heaviest, elements that behaved in similar ways kept appearing at regular or periodic intervals. Because of this, Mendeleev put together a table of the chemical elements with the ones that behaved the same listed in vertical columns. We call this table the periodic table of elements. Here's an example of one. Each box in the table lists a different element. The letters in the boxes give the symbol for each element. As I said, the vertical columns show elements with similar properties. For example, if you look at the column on the far right, all of the elements you see there, like helium, neon, and argon, are all noble gases that don't like to combine with other elements. This table and the properties of the elements in it are very central to chemistry. And if this were a chemistry course, we'd spend a lot of time going over it. However, in this class, I'd like us to focus on just 2 important observations. First off, the elements at the top of the table are lighter than the ones at the bottom. In other words, the individual atoms are heavier as you go down the table. Also, notice those 2 bottom rows labeled lanthanides and actinides. Those really belong in the rows above. You can see where a gap has been left to fit them in. We don't put them in there because they would make the table too difficult to show clearly on a single page. The other important idea is this. The elements at the top of the table are usually much more common than the ones at the bottom. There are exceptions here. Not all of the elements at the top are common. Ones like boron and beryllium are fairly rare. However, it does hold as a broad trend. This is a really important idea in astronomy, and one that will come up again later in the course. In particular, notice the two elements at the very top. Those are hydrogen and helium, and between them, they make up around 99% of the atoms in the universe. This leads us to a very important summary of astronomy. The universe is made of 3/4 hydrogen and 1/4 helium. That's the course. Any questions? If that's a little too simple for you, how about this? The universe is made of 3/4 hydrogen and 1/4 helium, but it's also slightly contaminated by heavier stuff. Of course, that slight contamination has some interesting effects that we may want to look at a little more closely. In fact, all of this should raise some interesting questions for the scientist in you. After all, the planet we live on certainly isn't mostly hydrogen and helium. Even the big hydrogen-rich planets like Jupiter and Saturn aren't 99% hydrogen and helium. So how come the planets have so much more of the heavier elements than the universe as a whole? We'll have to return to this question when we talk about solar system formation later in the course. Of course, much of what is interesting about chemical elements is how they react with each other. In particular, many atoms combine into molecules, groups of two or more atoms held together with chemical bonds. This produces compounds, and there are several compounds that are important in planetary astronomy. The first of these is water, a compound of hydrogen and oxygen. We also have ammonia, which is made of hydrogen and nitrogen. Next is methane, which is made of hydrogen and carbon. Notice something about these. They're all compounds of hydrogen, the most common element in the universe. In fact, oxygen, carbon, and nitrogen are some of the most common elements after hydrogen and helium. So it's not surprising that these form important compounds. We often group these together as the hydrogen compounds. We also sometimes put together their first initials and simply call them Wham. The next group of important compounds is the silicates, which are made up of silicon, oxygen, and often other elements like aluminum and magnesium. We usually call these compounds rocks, and they are very important building materials for planets. Another important group of compounds are the organics. These are based on carbon and hydrogen, but they often include lots of other elements such as oxygen, nitrogen, sulfur, phosphorus, etc. The simplest organic compound is methane. However, in astronomy, we also find complex organic molecules made of dozens of atoms, especially in the asteroid belt and the outer solar system. Finally, we have carbon dioxide, which is an important compound in planetary atmospheres. What is it that makes one atom different from another? An atom is made of just 3 particles. Most of the space of an atom is defined by the electrons. These are negatively charged particles that orbit around the center. They have almost no mass. You can treat the electrons as a sort of electronically charged fluff. However, much of chemistry is about the ways electrons in atoms behave. In the center is the nucleus, which is made of protons and neutrons. Protons have a positive electric charge, while neutrons have no electric charge. We say they're neutral. Protons and neutrons have roughly the same mass, and between them they have almost all of the mass of the atom. However, the nucleus takes up very little volume. It's around 100,000 times smaller than the atom as a whole. The protons are especially important. The number of protons in the nucleus is called the atomic number. It defines what chemical element an atom is. For example, if an atom has 1 proton, it's hydrogen. If it has 2, it's helium. If it has 6, it's carbon. If it has 92 protons, it's uranium. It doesn't matter how many electrons and neutrons an atom has. The number of protons defines it. In most atoms, the number of protons is equal to the number of electrons. Even though electrons are much smaller than protons, they have the same size of electric charge, just opposite signs. So if the number of protons and electrons is the same, then the atom is electrically neutral overall. If somehow they aren't equal, then the atom becomes charged, and we call it an ion. The electric attraction between the positive protons and the negative electrons is what holds the atom together. Here's a picture showing the structure of an atom. Most of the room is taken up by the cloud of negative electrons. There are only a half a dozen electrons in the atom shown here, but it's shown as a fuzzy mass because of the uncertainty of position of the electrons. This is one of the strange things we start to see on very small size scales. It becomes difficult to pin down the positions of objects. At the center of the cloud is the nucleus, made of positive protons and neutral neutrons. Once again, the number of protons, shown in red here, defines what element it is. In this case, there are 6 protons, so it must be carbon. Well, it's good to know the properties of individual atoms. We usually don't deal with atoms one at a time. Instead, we work with trillions of atoms at once. So we need to look at how big groups of atoms behave. First off, let's look at what we call the phases of matter. Well, your textbook discusses several phases. For our purposes, we're going to focus on the 3 most familiar ones: solid, liquid, and gas. Most elements or compounds can be in one or more phases depending on the conditions. The conditions that have the most to do with what phase matter is in are temperature and pressure. Changing either of these can change the phase. We usually think about phase changes in terms of water. This is because water is one of the few materials around us that commonly appears in all 3 phases: water ice, liquid water, and water vapor. However, most other materials can change phase as well. So what defines the 3 phases of matter? We'll look at how they behave on the large scale and on the atomic scale. Solids don't flow and don't automatically fill up spaces. In other words, they hold their shape. If you look at their atoms, you'd see each atom is tied to its neighbors. As we saw in the last chapter, all atoms are in motion. This is what defines the temperature. However, in a solid, that motion is very limited. All the atoms can do is vibrate in place. This is kind of like being at the front of a crowd at a concert. Everyone is packed up against the stage and you can hardly move at all. If you heat up a solid, it can turn into a liquid. A liquid flows, but it doesn't fill up a 3-dimensional space. In this case, the atoms are no longer bound to each other, but they're still very close together. This means that they can spin around as well as vibrate, but they still can't go very far without bumping into another atom. This is like being a little ways away from the stage of the concert. You're still in the crowd, but it's not quite so tightly pressed together. Finally, at still higher temperatures, a gas can both flow and fill up space. Now the atoms have room to move around past each other. We call this motion translation. This is more like being out at the back edge of the crowd, where there's lots of room to move around. Now it's easy to see why phases change with pressure as well as temperature. If you squeeze on a gas, it will move the atoms closer together and turn it into a liquid or even a solid.
In this question, you should start by filling in the blanks in the sentence with solid, liquid, and gas. Then you should think about real materials you have experience with that follow these rules, and also come up with some that don't. For any that don't, can you figure out why? Remember, the point here is not to do a big research project, but instead to think about your own experience with different materials in day-to-day life.
Changing phases always involves either adding or releasing energy. For example, you have to put energy into water to turn it into water vapor. Your body makes use of this to keep you cool. When you sweat, this puts moisture on your skin. As this water evaporates, it absorbs a little heat energy from your body to turn into water vapor, cooling you down in the process. Water ice also absorbs heat energy when it melts. This is why ice is so effective at keeping a drink cold. The ice is taking heat from the surrounding liquid as it melts. In any liquid, remember that the molecules themselves aren't bound to each other, so the only thing holding a liquid together is some outside pressure, like air pressure. This is why a liquid has to absorb energy to change to a gas. The molecules need the extra push to overcome the outside pressure and add translational motion to their spin and vibration. However, this means that if you put any liquid, like water, into a low enough pressure, it will boil away. With the air pressure gone, nothing is holding the molecules together, so they simply fly off into the surrounding space. Other materials do the same thing at different pressures. For example, dry ice is simply frozen carbon dioxide. The air pressure on Earth is too low for carbon dioxide to form a liquid, so it simply evaporates when it warms up rather than melting. All of this points out something we need to keep in mind as we study the solar system. Phases depend on conditions, so we shouldn't expect materials to always be in the same phases we're used to. On Mars, water ice evaporates the way dry ice does here. In Jupiter, the pressures are high enough that hydrogen is a liquid. On Titan, it's cold enough that there are lakes of natural gas. So we can't afford to have Earth-based biases about phases when we study the solar system.